Our session this morning is titled Suppression of Self-Excited Oscillations Through the Nonlinear Tuned Vibration Absorber, to be presented by Dr. Habib.
Thank you for the presentation. So, first of all, I should acknowledge my co-author, Professor Gaetan Kerschen, that we performed together this work. And this work is about passive suppression of self-excited oscillation through a nonlinear tuned vibration absorber. So, I think everyone here is familiar with limit cycle oscillation, self-excited vibration, which occur in many engineering systems. So this was supposed to be a video. This is a picture of a wing of an F-16 aircraft, but it's just an example of where we can find self-excited oscillation. We have also in automotive disc brakes, machine tools, drill sting system, just to cite some of them, but we have also in suspended bridges and high-speed train, as we saw today. And this is a very challenging problem in real applications. So, but there is a particular scenario which is especially dangerous. That is the case when we have subcriticality at the loss of stability. So, for example, you see here we have, if you have this situation, so as a linear analysis would mark the stable region and unstable region where we have self-excited oscillation. But due to this subcriticality, and nonlinear analysis will show that we also have B-stability here. So even if we are confident here that we have stability, then we can perturb the system, we can jump to quite large attractor, causing a serious problem even in real applications. And also, at the loss of stability here, we have a catastrophic bifurcation, so the system will jump immediately to a very high, very large periodic solution, which also can have very severe consequences. So we try to design, we designed a passive nonlinear vibration absorber, which should help not to have this scenario or improve the performance of structures in this case. And these had several tasks. So the first task that this absorber should achieve is to enlarge the stable region. So simply push the bifurcation to higher values of the bifurcation parameter. Here I wrote flow speed, but it could be whatever, so depending on the system we are considering. And this is related to the linear properties of the system. So since it's linear stability, so we will control this adapting the linear spring and damper of our absorber. And the second task is to avoid B-stability. So to avoid this supercritical bifurcation and enforce the system to lose stability through a supercritical bifurcation. And this can be done through correct design of the nonlinear characteristic, nonlinear spring in this case of the absorber. And then the last objective of the absorber is to reduce the amplitude of limit cycle oscillation. So even in the case where we have we are unstable, we have this self-excited vibration, we want to keep this vibration small in order not to create too much damage. Unfortunately, with our absorber, we don't have freedom left for target this objective, but I will show that still targeting the first two will also have obtained quite a good result in respect of the third one. So my presentation will go through these three tasks. So we start with stability analysis, and then I will go to the bifurcation analysis, making a local and a global investigation. The primary system we are considering is quite general, so we wanted to be as general as possible. So we use a van der Pol-Duffing oscillator. We see that the van der Pol term is related to the instability, so the fluid structure interaction. Here we have a negative linear damping, which causes the rising of the oscillation, while the Duffing term is related to structural nonlinearity of the structures, which means that increasing the amplitude of oscillation, the frequency of the oscillation will also change. And we attach to this system our nonlinear vibration absorber, which its particularity is that the nonlinearity is not specified a priori. So we have three coupling terms. One is related to the linear damping of the absorber, one to the linear stiffness, and this one to the nonlinear stiffness of the absorber, which is, for the moment, is not specified. So we keep it for the moment in this way. And then we go through the linear analysis, which as is already known in the literature, has been also the group of L'Aquila has worked on this. I should acknowledge them. And from stability analysis, so considering only the linear system, which is relevant for the linear stability, it is possible to obtain in closed form the optimal values of the damping and the stiffness of the absorber to maximize the stability. So we see that this is the stability chart. So we have stability below this surface, and you see a peak here, which means that here is the optimum we can obtain in terms of stability. And this is the bifurcation parameter, while epsilon is the mass ratio, and these are the parameter where we should tune. I don't want to, it's not important which are the values, but we can obtain in closed form the values which gives the optimal stability. So at this point, for our absorber, we defined these two parameters, so linear stiffness and linear damping, and we still have unknown the nonlinear characteristic of the absorber. To define it, we address the principle of similarity, which means that the nonlinearity of the absorber mimic the mathematical form of the nonlinearity of the absorber mimic the nonlinearity in the primary system. So in this case, we have a Duffing oscillator, the Duffing term, which is the structural nonlinearity of the primary system. So we impose that also the absorber has a cubic characteristic as the primary system. And at this point, the only unknown left is the nonlinear stiffness, the coefficient of the nonlinear stiffness, so this Kn2. To define this parameter, we make a bifurcation analysis. So we analyze the bifurcation occurring at the loss of stability, and in particular, we make a local analysis. So we reduce the system to a model which is valid in the vicinity of the loss of stability. And for this system, the system loses stability most of the time, most of the cases through Hopf bifurcation. So given the primary system, we perform many transformations. I have no time to go into details of this, but we make a Jordan normal form, then we make mainly a center manifold reduction to reduce the dimension, near identity transformation to eliminate most of nonlinearities, and then we obtain finally an amplitude system going in polar coordinates. So this is an amplitude system, which you see is extremely reduced. This is the normal form of a Hopf bifurcation. And all the bifurcation is characterized by the value of this delta. And if delta is negative, we have a supercritical Hopf bifurcation, while if delta is positive, we'll have a subcritical bifurcation, which causes B-stability. And of course, we want to have a delta negative, because we want to have a supercritical bifurcation at the loss of stability. So we analyze more in detail this delta, and from our analysis, we obtain that delta is given by the contribution of three terms. So this delta zero is related to the structurally linear system, while these terms in red and blue, these terms is related to the Duffing term of the primary system, and this one to the nonlinearity in the absorber. So if we see the evaluate delta zero, we see that it's always negative. This means that if the system would be structurally linear, so we consider Kn1 and Kn2 equal to 0, we would have that also delta would be negative. So we have supercritical bifurcation. It means that system with no structural nonlinearity in this case, would behave in a good way, in the way we want to obtain, so in a supercritical manner. Then we see the effect of delta 1, and we see that around this value, this K2 optimal, which is the optimal values of the linear system of the absorber, we see that delta 1 is rapidly changing from positive to negative values. And if we think to a real case, we will never be exactly on K2 optimal, but we will be in this area due to uncertainty. We won't be able to say if we are here or here. So this means that we don't know really the sign of delta 1, and this means that it's really hard to predict the effect of a nonlinearity in the primary system on the bifurcation. Then we analyze the delta 2 related, so the term related to the nonlinearity in the absorber, and we see the delta 2 has a very similar shape to delta 1, which means that also in this case we have, it's very hard to predict the effect of the nonlinearity in the absorber, but we see that there is a sort of mirrored pattern of the two. And this suggests that maybe even if we don't know the effect of each of the components, maybe we can use this mirrored pattern to have a compensation of the two. So maybe somehow this term can compensate this one. And I will show how this can be done rigorously through the analysis of another bifurcation occurring at the loss of stability. So this is so as I mentioned, the system is usually losing stability through single Hopf bifurcation. This is valid along the whole stability boundary, except on this line where we have a double Hopf bifurcation, which is related to the intersection of two branches of single Hopf bifurcation. So here we have, in some sense, we have a double loss of stability, and we have two couples of complex conjugating values which get positive real part. And we perform an analysis similar to the other one. It's slightly more complicated because we have a higher dimension, and this is the reduced normal form for a double Hopf bifurcation. Now we see that the system is not, the bifurcation is not defined by a single parameter, but we have 4 deltas which are characterizing the bifurcation. But the good thing is that this delta has a similar similar shape than we had for the single Hopf bifurcation. So also in this case you have 3 terms, one related to the linear and 2 to the nonlinear structural nonlinearity of the system. And our objective, as I mentioned before, is to have this term compensate the effect of this term. So these 2 terms should be equal to each other. And this can be, for a single case, it can be easily done. But quite interestingly, this equation is valid for all these deltas. So it means that if we tune Kn2 with respect to Kn1 in this way, so where only the mass ratio epsilon is important to define Kn2, we can obtain exact compensation of the effect of the nonlinearity of the primary system through nonlinearity in the absorber. And this is exactly valid for all the double Hopf bifurcations, so along the whole line of double Hopf. And it's valid in quite good approximation also if we move on from that. So if we are in a single Hopf in the vicinity of the optimal condition, still this compensation is valid with quite good agreement. And I will show some numerical result, but so if we consider this new formula as the tuning for the nonlinearity of the absorber, we have a full tuning rule for the nonlinear twin vibration absorber. So we find the optimal values of the linear stiffness, of the linear damping, and then through the principle of similarity, we define the exponent of the nonlinearity of the absorber. And then we define in closed form the optimal nonlinearity, the optimal coefficient for the nonlinear stiffness of the absorber. So if now we verify numerically the bifurcation diagrams, we see here you see in black, we see the case, the bifurcation diagram in the case of no structural nonlinearities. So as I mentioned, here we have a supercritical Hopf bifurcation, which is the favorable case. Then we introduce a nonlinearity in the primary system, and we see how this, this branch of periodic solution bends to the right and we have to the left, and we have subcritical bifurcation, which has also B stability. But if we add nonlinearity also in the absorber, according to the tuning rule, we can bend this branch again to the right and retrieve the supercritical behavior through adding this absorber. And another interesting result is the compensation. So we can see that this the blue curve and the black one are really close to each other. So it means that even, as I mentioned, the compensation is not exact in the case of the Hopf, of the single Hopf. So we impose a slight detuning with respect to the exact result, to the exact solution, to exact values. And still, we have this compensation with quite good agreement. So this is only the local picture of the bifurcation. But then we went to higher amplitudes. This is only numerical result. The analytical were only local. And also in this case, you can see how this, in the structurally linear system, we have this nice supercritical behavior, while the nonlinearity in the primary system is giving this subcriticality, and adding another nonlinearity also in the absorber, we can retrieve this supercritical behavior and have the compensation. And this is obtained considering a small detuning of the linear spring, so slightly less than the optimal values. But if we do the same for a linear spring of the absorber, which is slightly larger than the optimal values, as I mentioned, the nonlinearity of the primary system in this case is an opposite effect. So in this case, the nonlinearity in the primary system is helping to have supercriticality. So this is already supercritical. But still, at higher amplitude, the detrimental behavior, so the B stability, is still there due to this folding of the branch. And also in this case, the nonlinearity in the absorber is succeeding in avoiding this dangerous scenario. And also in this case, we have quite good compensation of the two nonlinearities. So to validate the principle of similarity, we made some trial using other nonlinearities in the absorber, considering still a cubic nonlinearity in the primary system. And even this is not a thorough analysis, but still we are not able to obtain as good result as that we obtained with a cubic nonlinearity in the absorber using other nonlinearities. And mainly because, as you see, a quintic nonlinearity at higher amplitude can do something similar to the cubic, but at lower amplitude, the quintic has no effect. So this, I think, it really can be read, the meaning of why you should use the principle of similarity, because we can have a compensation that works in the same way as in the primary system for different amplitudes. So the effect of the nonlinearities is increasing its importance in the same way for the primary system and for the absorber for increasing amplitude that we don't have if we have two different nonlinearities in the system. So to conclude, we presented a nonlinear absorber that has a nonlinearity not specified a priori, which gives additional flexibility, and we address the principle of similarity to define it. Then we made a full analytical design for a van der Pol-Duffing Oscillator system, which is quite archetypal system. And we show how this nonlinear tuned vibration absorber combines the strength of a linear absorber, which is able to push the loss of stability to higher values of the bifurcation parameter, but we also obtain a positive effect in terms of control of the bifurcation, which is something that the nonlinear energy sink can do. So we combine these two effects. And a work in progress is experimental validation of this effect that will be done through considering Vox-induced vibration on a horizontal cylinder in a wind tunnel. And another aspect that we are further investigating is this sort of passive feedback linearization that we found during our analysis. Thank you.
known that bifurcation control, which is the first one, that we can change from subcritical to supercritical, just introducing a nonlinearity without the mass. By putting the mass absorber with the mass in, the problem got complicated so much so that you have the double hub bifurcation and all of the other complications. But if you use only a nonlinear spring, which will compensate whether it's quadratic nonlinearity or cubic, you can change the bifurcation from subcritical to supercritical so that you don't need the mass absorber.
Mm-hmm. So you mean that basically
with the bifurcation, which we have similar things, but you put the nonlinearity. Say, let's take the, go back to the van der Pol, the original one.
Yeah, so
just add a nonlinear spring there in the system, or nonlinearity in the system, compensate for that cubic, and that's done. And the bifurcation control will change. So that for the airfoil and for the flutter and so on, you don't need the mass with the complication, and if you have a wing, you add a mass and you add the other double hub bifurcation. Just put the nonlinearity in a spring nonlinearity or feedback nonlinearity on the basic system.
I agree that if we add the nonlinearity here, we can control the bifurcation for sure. I think that if we don't add the mass, we cannot push the bifurcation. So we can actually control the bifurcation. We can have a nice loss of stability. Let's say we can control.
You're pushing it with linear feedback. You have linear feedback without the mass.
Yeah, for sure.
Forget about the mass. Linear feedback with the constant term. You have with the spring term, with the damping, damperance, without the mass. The mass got you so much complications with the hub bifurcation and the complication.
I agree that if we can play with the primary system, we can really we can really improve the scenario. But my assumption is that the system is given, the primary system is given, and we can add just some small systems. So I consider that the mass of the absorber is 5% of the mass of the primary system, but I could consider even smaller. And I believe that we can still obtain quite good improvement in terms of stability. Of course, if we can play with
You have an airplane and you have a mass which is 5% of the mass of the airplane or the mass of the wing, you lost so much. You don't want to do it to add mass to it. You put passengers, you put bags, so you put other things, okay? And you don't have the double hub bifurcation.
Yeah, I agree. With airplanes, it's quite. I mean, there are many restrictions. So I say for other kind of application, probably is more appealing than for airplanes, which is quite special.
Actually,
we have another?
My question is related to that one. What is your ratio of M2 over M1?
Excuse me?
What is the ratio of M2 over M1?
I consider 5%, 0.05,
okay.
but can be even less and
so
still work.
I think actually, even though you changed it to supercritical instability, you might actually still see the subcritical instability as you move a little bit higher in the flow speed. You did not change it for the whole domain. I think at some point you're going to pick up multiple solutions and the subcritical instability is going to come back.
If I have a strongly nonlinear, considering this model, if I have a strongly nonlinearity in the primary system, I actually still have B stability because I make something which is perfectly working here. I don't have any B stability here at the loss of stability. But when I'm here inside this region, so I'm still in the stable region, the B stability is coming from some subcritical bifurcation that I have here on the side.
Yeah. So
this can really happen.
And the other thing that, I thought the idea of nonlinear energy sink or tune is to be able to respond to any frequency, control any frequency. But when you put the linear part, you're controlling one frequency now. So what's the advantage of what you're doing?
Thank you for the question. I really want to show this. that okay, I show you what the maximum you can do with a linear absorber. So this is what so this is a different perspective. I'm sorry, but still this is the bifurcation parameter, and this is the maximum we can obtain only with a linear absorber. And instead, if we use a nonlinear energy sink, so we don't have a linear spring. So this is the values we have with the basically we have this. So we lose stability here, which is square root of the value we have here. I mean, mu1 is 0.1, so square root of 0.1 is 1/10, something like that. So, so I think the use of the linear spring is critical, in my opinion. And if we don't use a linear spring, we can play with the bifurcation, but we really cannot play with improving the linear stability of the system.
I hope you'll get a chance to see them.
Yes,
Because,
yeah, for sure.
Yes.
It'd be
Thank
nice.
you.
Any other quick question? Yes, please.
Short question. Could you explain me what parameter defines the flow speed? You mentioned flow speed, which is what is in your original equation?
Yes. So in the original equation is C1 will be adimensionalized, and it's C1 basically. And I called mu1 because I made some, yeah, van der Pol, yes.
Quite a bit. This is basically a wake oscillator what you have. The wake oscillator, you don't model the flow. You just assume distributed van der Pol there, which is far from basically from true. Because we try to calibrate, and you really have flows. It's only good when you have a laminar flow. Once you go to turbulence, you're gone, basically. So if you're thinking about the realistic model, van der Pol probably is not the best.
I agree. So van der Pol is, we have, if we consider force-induced vibration, we have a different phenomenology. We don't have a Hopf bifurcation. We have a double, we have a codimension to bifurcation different for a van der Pol. We have a couple of exactly zero eigenvalues at the loss of stability in case of force-induced vibration. And is a sort of resonance that we have with the wake, with the cylinder. So it's quite it's different phenomenology. I made so this analysis, the bifurcation analysis, won't work in that case. I made some numerical investigation considering parameters similar to this one, but the correct tuning is not really necessary. But quite similar tuning is still working very well, and I was able, I mean, I don't have the result here, it's a work in progress, but we were able to almost eliminate the resonance on the cylinder in case of a linear cylinder with a linear absorber, while introducing a nonlinearity in the structural system. A linear absorber was having some problems, so we had some isola of instability, and the nonlinearity in the absorber was able also to eliminate those isolas. So I'm sorry I don't have figure to show you this result, but thank you for the question.
Well, just to stay on time again, thank you, and let's thank all the speakers. I guess this concludes.